Okay, so part A for this graph of h of x. What is h evaluated at? Let's just say 4. I'm going to pick a bunch of different questions. So this is not even calculus. This is just plain college algebra material, evaluating a function. When the value of x is 4, what is its output? You can see. Go straight up. We're about right there, right? So that's the order pair 4 comma 5. So this is just equal to 5. Put a different color, something that might be a little easier to see. B, what is h when x is 3? So x is 3. Is it right here? 6? Nope, it's right there. 8, right? Because it's the closed circle. That means that is the specific point on the function, right? So this is equal to 8. So our ordered pair right here is 3 comma 8. Now if I say, what is h of 7? So here's 7. Does not exist. Is undefined. There's no point on there, right? So let's just put undefined, does not exist, however you need to say it. All right, so a lot of those functions evaluate out to a specific y value, right? Perfectly fine. Some of them give you undefined, perfectly fine. Now when I take the limits, say the limit as x approaches 3 of h of x. All right, here's 3. Now again, a limit is the idea of approaching, not equal to it necessarily, right? Getting closer and closer. So you, in a sense, evaluating numbers that are like 2.999, 3.0001 to see what their outputs are close to, right? So those values I just said, their outputs would be very close to 6, right? Think horizontally as the x is moving from the right. Okay. The y value is getting closer and closer to 6, right? As the x value is moving to the left, from the right, if you want to say it that way, x is getting closer and closer to 3 from the right side. You're getting closer and closer to 6. So that's 6 right there. What is the limit as x approaches 4 of the function h of x? I'll put this one in green. All right, so h of 4 is equal to 5, right? So the point does exist. There's no hole on it. And the same thing as you're approaching 4 from the left, think about going horizontally, closer and closer to 4 from both directions, the y value is still 5, right? So in that scenario, the function evaluated at 4 is actually the same as the limit as x approaches 4. And one last scenario we could look at. What is the limit as x approaches 7 of h of x? So as we're getting closer and closer to 7, the y value is close to. That one's 2, right? The evaluation of it at 7 was undefined, but the limit still exists because you're not looking exactly equal to 7. You're looking at values that are close. Right, so any questions about that? The visual approaches to limits. The calculus approach and the algebraic approach. Those are much easier because you know some functions, their graphs are really strange, right? and it's almost impossible to see holes even on a graphing calculator or anything like that. That's where calculus comes into play. It's things you can't see, but in the real world, you can figure out solutions to them. All right. So we got to continue on to 2.2, wrap up that section. And we're going to see something really interesting later on. One of my favorite things. It's called the squeeze theorem. It's pretty neat how that is derived. So 2.2, definition of limits. We're going to continue this. All right, last, I think we left off with a graph that looks similar to this, and we did one that had some radicals involved, and I showed you a little technique on how to figure out the limit algebraically. We're going to see lots more of those. So the next topic we have is called one-sided limits. Yeah, I don't want to bore you with definitions and things, but the concept of one-sided limits, we just did it. If I'm looking at a graph, saw how I could approach the value of x from both directions, right? And they're meeting out at a similar common point, right? Now I don't have to look at it both ways. I'm just look at it from one way. And the way we're going to do this is the limit as x approaches some number, a, let's call it, and if I put a little plus like this of our function, which equals our limit value L, this says x is approaching a from the right. Okay. This is called a right-sided limit. Okay. So suppose this is our function f of x. And this says if I want to say what is the limit as x approaches 3 from the right. I'll just look at it coming from the right. So coming from the left, coming from the right, heading towards the left, you're approaching this y value of 1, right? That's it. Now, if I want to note it coming from the left, the limit as x approaches a from the left, you put a little minus there, of f of x. So equals L. This is x approaches a from the left. This is a left-sided limit. So that same graph, if I use the limit as f x approaches 3 from the left would be what? 2? Yeah. Going from the left this way, approaching that y value of 2. Now for this particular example, if I write it like this, The limit as x approaches 3 of f of x. I don't indicate which direction, right, I'm coming from, the left or the right. If there's no indication, that means it is understood it's coming from both, okay? So no plus or minus indicates limit or the value that x approaches. Let's just put it this way, x is approaching. Three from both sides. Well, we just saw coming from the right side. The limit was equal to 1. Coming from the right side, the left side, going to the right, the limit was equal to 2. Since those are two different values. The limit as f approaches x approaches just 3 does not exist. We have to go to the same value. It does not exist. Any questions? All right, so we'll do some more examples like this in a minute. We're going to put a lot of other concepts together and put it all together and evaluate and see what happens from there. So that's the end of 2.2.